so I'm not going to give some proofs. So take a section here. We're going to take these guys to be sections here, and then we're going to take here to be a derivation. And what I want to show is that I want to show linearity after. I want to show that it's a genuine endomorphism. So I want to show that that we get an endomorphism of f of O of x modules. Okay. Like so. Okay, so this is what I want to show. And to show this, so additivity is easy. This thing by definition looks like this connection to the P minus, and both of these guys are additive. So to show linearity, we compute each separately. Compute each separately. Okay, so what do I mean by this? So we do this. Yeah, we take this guy. We apply it to FV. And we use the rule for connections. So then we have F. Okay. Similarly, we're going to do the other one. And this one we use the 0 to P. So we do theta to the J of F, and then we have this thing, and then we have P minus J of V. Okay, so we use this Leibniz rule, but since we're working in characteristic P, they all go away. So this is theta P of F, this thing to the 0 with a V, which will just be V plus, then we have F, this guy here to the pth power of V. Okay, so that's what we have, and then we can notice that when we're going to subtract these two to get the full thing, so this thing minus this thing is the P-curvature, and this term and this term are the same. Okay, so when we subtract them, we get the desired result. So so this tells us that of theta of FV. So this is going to be equal to, well, let me just write out the definition again. Theta to the P. Okay, and this becomes what? So this becomes those two things that get subtracted. So let me go back up here. So these two cancel. So the two underlined pieces. And then we get F V minus F, it's the P of V, like so. And so this is just F of theta applied to V. Okay, so that shows us linearity in the second component, and so this tells us that, so i.e. that this guy here, when we take a theta, is actually an endomorphism of X modules of E. Okay, so next we want to show the following, that plus theta 2 is equal to f to the p plus theta 2. Okay, and so this breaks up into two parts, like before. So the additivity will be implied by Jacobson's, and then the semilinearity, this will come from Deline's formula. Okay, and so let me show you how to do these. So again, we can write down the two different formulas. So the proof, proof of additivity. So now what we'll do is we'll take, let's see, so I have my little cheat sheet here. So so what I do is I take theta 1 and theta 2 derivations. Okay, and what we'll do is we'll take Jacobson's formula. Okay, so this thing says that this is theta 1 to the p plus theta 2 to the p plus I is equal to 1 up to p minus 1 of si theta 1 theta 2, and these guys here are Lie polynomials. Okay, so we have some universal polynomials for here. Since they're Lie polynomials and this thing is integrable, so i.e. that theta 1 theta 2 is equal to theta 1 theta 2, i.e. this thing, we can apply this guy, and what do we get? So when we apply this, theta 1 plus theta 2 to the p is equal to theta 1 to the p plus theta 2 to the p plus, and then here I is equal to 1 up to p minus 1 si, and then this uses the integrability here, that we get that this is a morphism, that the nabla is a morphism of Lie algebras. Okay, similarly, we can apply Jacobson's formula to this guy. Okay, and what do we get? So we get, so we have theta 1 plus theta 2. We have these two elements, and we take it to the pth power. And so we get this is to the pth power plus this guy to the pth power plus to p minus 1. Okay, and now we can subtract the two expressions. So so what do we have? Minus so this is equal to, well, now we can see that this one, we have this one here, and this is equal to this one here. And so we should notice that this thing here is, by the way, plus theta 2. Okay. So this whole thing, when we subtract them, this is psi here. Okay, and so now when we subtract them, these two things cancel, the two underlined pieces. This is theta 1 to the p plus theta 2 to the p minus, and then we have over here the two other pieces. P, like so. And so breaking these up, we get plus as desired. Okay, so we started with here, okay, and then using Jacobson's formula twice, right, we can write down two different expressions, and we end up getting that it breaks up. Okay, so that shows additivity. So additivity uses, again, additivity uses Jacobson. And now, so this is what we just did. Now we're going to do this one here. So the semilinearity. Okay? Okay, so the proof of semilinearity to do this, so take theta, we'll take g and o of x, theta to be a derivation, like so. And so we'll first apply, so we apply, so we first apply Deline's formula to g theta. Okay, so we have g theta to the p distributes almost plus, so we have g times, then we have this adjoint action, p minus 1 times on the p minus first power of g theta. Okay, and then we take nabla, so we're going to put this in the subscripts, g theta to the p, and then we have g to the p theta to the p plus g dot adjoint action g to the p minus 1. Okay, and there was a remark I made way earlier about the adjoint action in these derivative rings, and it's here. It says that if you do the adjoint action of a derivative on x, then this is just saying the derivative here. So in particular, the adjoint action, if I do it p minus 1 times on x to whatever power, so this will be the p minus first derivative of x, since you're just going to be iterating this operation. Okay, so that's what this is actually going to do. So this now, now what do we get? So now we can use the properties of the connection. So this is g to the p here, theta to the p plus, and then we have this connection. Now I'm going to take the connection of this whole thing. Well, let me write this out. G adjoint action. Then I'm going to replace it in a second. Okay, so this is g to the p here plus, and then this is g, and now I have theta to the p minus 1, g to the p minus 1 here, theta. Okay, so we took the connection of this, and this is the resulting formula that we get. Notice that this thing here is, well, this is what it is. Okay, so what do we do next? So we're going to apply the same formula. So this is this. And now we're going to apply Deline's formula again. Now to G and this guy. Okay, so what do we want to do? We want to do G, this connection to the P here. And it says it distributes. But we have this correction factor where we need to do G times, and then we do the adjoint action of this to the P minus first power here. And then we have this guy here. Okay, and so again, this thing is just going to be the derivative of p. So it's going to be this operator applied p minus 1 times to this. So actually, this is just going to be g to the p plus g, and now we have again theta to the p minus 1, since the connection applied to these constants is the same thing. Okay, now we can subtract the two. Okay, so we have this and this. And so now we can put everything together. Okay, so when we put it all together, so let me get rid of that. The P curvature. Okay, so what is this? Theta to the P, which we computed, and then we have this one, theta to the P, which by the way is equal to, okay, so this thing here, okay, so I don't know what I want to say this, how I want to say it. Okay, so this is this g theta to the P minus, and then we have g theta to the P. Okay, sorry, this one needs to go down here. Okay, so we used Deligne in 2 places. We used it here and here. Okay, and and then when we applied Deligne's formula, we're going to see some similar terms, right? We're going to see that this term here and this term here are exactly the same, so that when I subtract them, they're going to cancel. And then we have these powers here that are going to be left over. And so this is equal to, the first one was GP, theta to the P, minus GP here to the P. Okay, and this whole thing, so this is just equal to GP, this thing, theta. Okay, so what it showed is that this part is equal to this part. That's what we proved. And that's what we wanted to prove. That's what we set out to prove. We set out to prove the semi-linearity from Deligne's formula. That being said, I'm gonna turn this off and then use this in the next videos.